Welcome everyone to Invent FM. It is my privilege to be joined by Aaswath Raman, an assistant professor at UCLA and the co-founder and CSO of SkyCool. Aaswath, welcome to the show.
Hey, thanks for having me.
Awesome. So I know you have a varied interests and a lot of things going on, and I would love for the folks to just get to know you a little bit before we dive into this specific invention we're going to talk about today, which is the daytime radiative cooling. But yeah, could you just tell us a little bit about your scientific background and now that you're a professor at UCLA, some of the projects and areas that your group is working in?
Sure. So my background's really in the field of optics and photonics. So historically, that's been a field that's been primarily concerned with, I guess, like fiber optics, optical communication, stuff like that. But when I started my PhD back in 2007, people really became interested in taking ideas from that field into energy applications. And so that's kind of where the vast majority of my work kind of sits. It's at the intersection of ideas from the world of optics, and in particular nanoscale optics, and connecting that to making some tangible improvement in some aspect of the energy ecosystem. So from a research point of view these days, part of there's pros and cons to being an academic, but one of the fun things is getting to explore a sort of more speculative ideas, things that don't necessarily need to meet the commercial stress test right away. So our group thinks a lot about controlling thermal radiation and thermal emission in general, partly motivated by applications, but also kind of from a more fundamental point of view, like what are new capabilities we can envision, what are the physical mechanisms that underlie these kinds of capabilities. So we're talking about things like spectral and directional control. And those applications go beyond energy. I think there are a lot of aerospace and defense applications. I now live in LA, and one thing that's really interesting about LA is it's got a huge aerospace industry, which is really interesting to interact with. And there's a really rich and long history of that. In addition to that, I've always been interested in some more physicsy, I would say, quote unquote, basic science stuff. I'm not really a physicist, but I pretend I'm one. And so, photonics is naturally the home for a lot of people who come from more of a physics background, but are interested in applications in some sense, either immediately or maybe decades in the future. And finally, one other thing is, before I did all of this, I actually worked at Microsoft for a year as a PM. I originally started out as a CS major when I was an undergrad. Back when, and I remember I was in a machine learning class, which only had about 15 students in it. So this was when machine learning was decidedly unpopular. And then, all these things happen. But so I've kind of come full circle on that. And we actually have a really interesting research program now. And I have lots of students, including a bunch of undergrads who are interested in this, where we're using a lot of machine learning techniques to both design and try and understand the behavior of these nanoscale optical materials and metamaterials. And it's still early days, but I think there's this really fundamental problem in that field, which is, how do you actually make your optimal material given some target functionality? And this is a bigger problem in material science in general, but from the optics specific domain's perspective, this is like a notoriously hard problem. And so there's what's really interesting there is there's both interesting science, but if you can make it work, I think there are a lot of people in industry these days that are interested in that stuff. So that's kind of a bit of where the group's at. But we're still thinking about radiative cooling too. Certainly from like a more speculative kind of out there ideas, not the kind of stuff the company's working on necessarily, but that maybe is a natural segue to talking about that in particular. So.
Okay, awesome. Well, you want to dive into to SkyCool and the big problem of radiative cooling?
Sure. So our company's vision, that, the company itself, Skycool Systems, was founded in 2016, and its vision was really to be a part of every cooling system on Earth and to make every system on Earth more efficient. Um, and why did we care about this? Well, I think if you think about cooling today, pictures like this might come to mind. So this is a picture of an apartment block, I believe in China. And one of the most remarkable transformations with respect to the prevalence of these systems is the fact that, just a couple of decades ago, much of India, China, Sub-Saharan Africa had very few air conditioners. Like, it was meant for, the extremely wealthy and privileged. But that's really changed, right? So that one of the biggest transformations we're seeing now is that, along with other appliances that you might think of as convenience, like refrigerators and microwaves, air conditioners are now, one of the most sought after technologies that a family that's entering the middle class in one of these countries wants to purchase, right? So,
Mm-hmm.
and it's totally understandable, right? I think, for example, India, where my parents are from, it's it is a warm place. It, in fact, some of the cities in India have requirements in principle for air conditioning throughout the year, and more cooler temperatures, comfortable temperatures, aren't just about feeling nice. They're actually tied to productivity, to health, to not suffering heat related illnesses or death during heat waves. So it's right. It's we often, I think, tend to think of air conditioning as just, well, part of our everyday world, but we don't necessarily think about how it's really changed the US itself. And so it's made so many parts of this country livable. And correspondingly, I think for a lot of folks around the world, it's just this part of this basic aspect of modernity, right, that people want to have access to.
Mm-hmm.
So if you think about cooling, though, it's not just about air conditioning. It's about all components of our industrial system that needs some degree of cooling for either because they're dealing with perishable goods like refrigeration systems, or they're just warm components. So that brings data centers to mind. And I'm just highlighting a few examples here, but there are a lot of other examples of these systems at the industrial scale, right? You find versions, components of cooling systems at power plants, at any number of industrial process facilities. So it's really everywhere throughout our world, and is therefore a big consumer of the electricity we generate today. So if you add it all up, it's about 17%. And what's really interesting about some of these users of electricity is they're really persistent, right? If you think about data centers or refrigeration systems, particularly supermarket or cold chain refrigeration systems, these things are on throughout the day and throughout the year. They have to be.
Mm-hmm.
So that makes it a really hard problem from an energy point of view as well, right? So there's
Yeah.
obviously you might be able to use solar, you might be able to use this or that, but some of the these are consistent users of electricity that are going to be around, and they're likely going to be around for a long time. I mean, there's no way, especially for refrigeration. There's we're going to likely use some version of vapor compression for the foreseeable future. I would bet for the next 100 years.
Right.
So there's no way around that. And today, all these systems added up contribute to about 8% of global greenhouse gas emissions.
Wow.
And so the obvious source of these emissions are, due to electricity generation itself, but there's also another source, which is due to refrigerant leakage. So
Mm-hmm. The CFCs leaking.
right. So the CFCs were banned with the Montreal Agreement in 1989, or the Montreal Protocol 1989. But the replacements, which are HFCs,
Oh, sorry. Okay.
it's they're better. They don't damage the ozone as much, but they do still have a heat trapping effect, and it's per gram of the HFC refrigerant, the trapping ability is 1,000 times more than CO2, depending on which refrigerant you're using.
Wow.
So these refrigerants leak pretty often. One statistic that may be a little old now was that, in a typical supermarket, the refrigerant, they've got these cold cases that sit where you go and buy your frozen stuff, right? And then they've got a condenser or a compressor in the back and a condenser usually on the roof. So there's lots of pipe and there's lots of refrigerant going there. And so there's a lot of mass volume of refrigerant. And it turns out about a quarter of that leaks in a typical year in a typical supermarket. So that's
Really?
a lot of refrigerant, and that, every little leak there actually traps way more than equivalent carbon emissions. So
Yeah.
roughly speaking, about 25% of the equivalent, CO2 emissions that are attributable to cooling systems is due to direct leakage of these refrigerants. So there's this really big push, which fortunately I think the US is also signing on to very soon, which is called the Kigali Agreement, which is meant to be a follow-up to the Montreal Protocol, where they're trying to essentially phase these refrigerants out as well and move to even, what are called natural refrigerants. And one of those is CO2. But there's all these alternatives. So there's, and we as a company interface with this segment, but it's this other big long-term trend in cooling that I think is super interesting, which is the move away from these traditional refrigerants to so-called natural refrigerants, which will actually have a huge impact, right? We're talking about potentially about 2% of global greenhouse gas emissions, which is a big number if you can actually completely
Just to switch that.
Yeah.
Oh, wow. So the HFCs are 2% of the 8%?
They're about a quarter of the 8%.
Got it. A quarter of the 8, so about 2. Got it.
Yeah.
Cool.
The exact number is probably maybe a little lower. I'm not exactly sure, but
Yeah.
The general rule of thumb for a typical traditional cooling system for the CO2 impact is about a quarter due to direct leakage of refrigerants, and the other 3/4 is due to basically the energy source.
Right.
So if you have a power plant that's polluting, so
could that 6% be fixed with? Would that 6% go away if it was 100% renewable electricity?
In principle, yeah.
In principle, okay.
Yeah, and so, we get this, and I'll get to this question of how you think about everything I'm going to talk about with respect to renewables and solar.
Right.
And I think there's an argument. There's a reason this all makes sense together, but I'm sure people will dispute that.
That's okay.
Yeah. And I think, this is actually part of that argument, which is that the reason you should care about efficiency is not what the situation is today, it's where cooling energy demand is expected to grow, right? So it's basically primarily driven by India, China, Southeast Asia, and to so far a lesser extent, Sub-Saharan Africa. There's just skyrocketing demand for cooling systems. And it's not just air conditioners, it's also a lot of countries are establishing cold chains for the first time or augmenting them. So, the supermarket, as we think of it, is a relatively recent invention or, product of modern country, like relatively developed countries. But it's now pretty much everywhere, right? So that means more and more people are consuming goods that need to be kept chilled, often frozen goods. And ultimately, this is all good because this provides a lot of stability for food supplies. There's a lot of, this is all ultimately good for us as humans, but it just means there's just going to be a lot more need for cooling energy. I think this is now widely understood and appreciated, is that we can't really hit the 1.5 C or even probably the 2 C target for warming if this skyrocketing trajectory continues and the systems stay the same, right? The amount of energy we're talking about is staggering. Like for India alone, I think I had gone to New Delhi for the launch of the Global Cooling Prize, which the Rocky Mountain Institute developed along with the government of India. And some officials there were saying, something like they'd need 300 coal power plant equivalents just to meet air conditioner demand in some part of India, like by 2040 or something like that, right? So
Wow.
that's a lot of power capacity they need to put out into the field. Obviously, there's a ton of solar going up, but you're trying to both replace existing fossil fuel plants and meet growing demand at the same time. That's really hard.
Yeah.
We're talking about deploying renewables on a scale that has rarely been done for any technology, right? So
Right.
I think, and so that's why I think a lot of us who think about energy on the thermal side really do believe that thinking about energy from the heat perspective, um, from the efficiency point of view, is going to have to play a big part in this, because that's a joule of energy you don't need to generate, and that makes it more plausible that you can get to 100% renewables.
Got it.
So I preview the next slide. And so I should explain that, I didn't come to this, this did not, strictly speaking, motivate why I ended up working on cooling at all, right? I learned about all of this after I actually started working on the technology. So back in 2012, I was finishing up my PhD at Stanford. And so I was thinking a lot about what I wanted to do with my career, what I wanted to do as the next thing. I had spent much of my PhD thinking about how you could use ideas from optics and this field called nanoscale photonics to make solar cells better at absorbing light. And the reason I had started working on this was around 2007. There was this trajectory where silicon prices were skyrocketing. And so in my case, millions of dollars weren't lost, but I think a lot of other people made a lot of bets on next generation solar technology because they thought this was a long-term trend. For me, it was just more like, well, from a research point of view, maybe we need to figure out how to make much thinner solar cells.
Yeah.
And I was really interested in that because I thought there would be an opportunity to maybe commercialize aspects of this. This seemed really, connected to what was happening with solar at the time. I was in Silicon Valley, so you saw these solar startups, and it was really exciting. And I thought, hey, this is great. And by 2012, unfortunately, silicon prices were crashing, and a lot of these companies faced, a very difficult market. Most of them, I think, didn't really make it. And so I was trying to figure out how I could connect my interests on the technical side with my longer term hope, which was to do something in the energy space, and particularly in the climate and energy, and at the intersection of the two of them. And so a lab mate of mine named Eden Raffaelli, and I we'd been discussing a lot of ideas, and we came across these old reports of a concept that was called radiative cooling, or colloquially sky cooling. And so a lot of the early references to this actually came from some people who were studying some archaeological sites. So these are actually a picture of a couple of them. So they're called ice houses, and in Farsi, the word is yakshal. So they're mostly located in the southwest of Iran, which is a very dry, arid climate. And they're I believe, about 500 years old, most of the ruins of them. And so the people that operated these many hundreds of years ago lived in a climate where, it got chilly in the winter, maybe around 45 degrees, 40 degrees at best, but it never actually got to freezing. But they were still able to somehow make ice in the desert, even though it never actually got below freezing, right? The air temperature itself didn't get below freezing. So the natural question the people that discovered these sites had was, well, how did that actually work? How were they actually able to take water and freeze it without any active energy input, and in a climate which would seemingly not allow you to do that? And the way it worked was actually dead simple. So you'd basically, in the example pool you see on the left there, people would pour water into these flat pools. And so they'd be really flat and relatively thin pools, and they just leave it overnight and it would freeze. So, okay, neat. They all probably observed this, but as scientists, you've got to ask, wait, how did it actually freeze, right? Like, what is the underlying mechanism here? And so the underlying mechanism here turns out to be the fact that that pool of water is facing the sky. As strange as it sounds to say that, it's literally because it is looking up, and what it's looking up towards is the most of the hemisphere of the sky. Obviously, it's a little blocked on one side, but it's got pretty good access to the whole of sky. And so, and we'll get into the specific technical details of how this works. But one thing I wanted to mention for anyone who's interested in kind of thermal storage or insulation in general, the buildings at the right were really interesting. They actually dug under the ground, and they would store these ice blocks under the ground. And because of the shape of this funnel, it would basically not allow warm air to really get to the bottom. And so this would basically preserve that ice all the way through the summer months. So they could have iced beverages or keep things cold through the summer. So it's kind of an example of
seasonal. Is the top open so the hot air goes out the top?
Yeah, that's my understanding. The top is open. And there's some pictures you can find online of them in the inside, but it's basically like a little funnel going up to the top.
So can I ask a question? Were there, as far, I don't know that much about the like archaeological side of this, but were there any, as far as you know, were there any use of like lenses or optics in this, or it was purely just these pools open to the sky? Because I had heard some story that there was some crude, optics involved in the right. You have a similar, what do we, if you have a telescope, right, you can like frost over the glass through the same effect. But
yeah, there's nothing that a conventional kind of lensing system would give you to because of the nature of thermal radiation. Is kind of just a hemispherical thing. So I wouldn't have I don't think as far as we know, they did nothing on that front. It was basically just put out pools of water. And to be honest, I suspect when they were doing this, they didn't really have reliable temperature measurement either. So it's not that they necessarily knew that it was above freezing in the air, right? But that the ground was below freezing, which is and that the pool of water was below freezing. So it was likely due to trial and error and experimentation.
Yeah. Okay.
And so, you can observe this effect yourself if you, for example, on a clear night, you park your car half under a tree and half not facing the sky. If it's not super dry, if there's some humidity in the air, you'll find water condensed on the sky facing side and a lot of dew formed, but the part that's under the tree will have no water condensed on the surface. And similarly with frost, right? Like, so that's why, if there are ever frost warnings, the simplest thing to do is just to cover the plant. That will block the plant itself from getting as cold, although it provides some insulation too. So it's not a perfect example, but the tree example is, I think, the classic one. You'll find, if you do a Google image search, you'll actually find a lot of photos of this example where someone's parked a car, half of it's dry because it's under the tree and half is not. So,
okay, so tell us how it works. Sorry, I interrupted. You were right to about to.
Yeah. So, well, I mean, let's think about it, right? So you've got this pool of water. It's looking up to the sky. So what is it about the sky itself? Well, that pool of water, like all objects on Earth, for the most part, pretty much all objects on Earth, emits heat away as something called thermal radiation or black body radiation. So this is kind of a basic feature of nature that, if you're at a particular temperature, you are giving off your heat as light, so electromagnetic waves or photons, however you want to think about it. And the precise wavelength at which those photons are emitted, the precise wavelength range, I should say, will depend on your temperature. So now, if you're thinking about that surface, that surface that's in the pool, it's actually sending up, therefore, its heat as infrared light. And we'll talk a little bit about what part of the spectrum is involved, but it's sending its heat up as infrared light upwards to the sky. Now, the sky contains our atmosphere as a whole, and the atmosphere blocks a lot of this, and it absorbs it, and you get heat back from the atmosphere. And so that's due to greenhouse gases, right? So that's what we typically mean by greenhouse gases. Those are gases that at particular wavelengths of light will absorb and re-emit the thermal radiation that's coming up from the ground. But for about 30% of the heat that's going up on a clear night, that heat effectively escapes. And the place it escapes out to is, well, space. So it's what's outside our atmosphere. So the simple story we often say is that radiative cooling is really taking advantage of sending heat to space. And this always, I should say, whenever people hear that, they're like, oh, are you beaming the heat to space or doing something? It's like, no, let's step back. Our planet as a whole is doing this all the time, right? So this is part of the Earth's energy balance, like all objects, for the most part, are radiating heat up. Some's trapped, some of it effectively escapes out. It's the part that doesn't come back to that pool of water that allows it to therefore cool down. It's the part of the heat that is effectively sent away that allows the pool to cool down. And I mean, the actual heat balance and all that is a little complicated, but the net result is that pool of water cools down such that it gets to the freezing point, and then the water freezes, and then you can collect it in the morning. So that's the core effect. And so to understand this, again, thermal radiation is not necessarily that well understood in general as a concept, but it's ubiquitous. It's around us all the time, right? So the best example of this is actually sunlight. So the sun is at a really hot temperature, and its surface can be effectively treated as what's called a black body. So that means it sends out heat. Its own heat is emitted as thermal radiation, but because the sun is so hot, it's at wavelengths that we can see, right? It's at these visible and UV and near infrared wavelengths we can see. Most of us here on Earth are much colder, right? So our temperature is around, let's say, 30 degrees Celsius, so about 90 degrees Fahrenheit. And so our emitted thermal radiation, the heat that we're constantly giving out to our surroundings, is at what's called the long wave infrared part of the spectrum. And the way you can detect that is through these thermal imaging systems or thermal cameras. So these cameras usually are designed to operate between 7 and 14 microns, although there are other systems that'll operate at shorter wavelengths. And so they basically pick up a good chunk of the heat that all of us are emitting. So if you can buy these from a company called FLIR as an attachment to your smartphone, and you can go around looking at stuff, right? You can see what everyone's temperature is to some degree of accuracy, but you can also pick up the fact that your walls are at a particular temperature and they're sending you heat as well. And kind of one fun fact here is that about 50% of your thermal comfort level, of the heat transfer that's associated with us as humans in like an indoor space, is due to thermal radiation, right? It's due to us interacting radiatively with the walls, the floors, and the ceilings. Like all parts of our body are actually radiating and are in exchange through electromagnetic waves with all these things that are around us right now. So it's this
And
basic part of nature we take for
that
granted.
the balance of that would be like convective or perspiration or
Yeah, so convective and due to evaporation, it will obviously depend a bit on whether you're exercising and like whether it's windy if you're outdoors. But a general rule of thumb is if you're indoors seated and in a sedentary state is the word, I guess, you're not doing anything.
You're doing what we're doing right now.
I'm doing what we're doing. You can attribute about 50% of the net heat flows due to thermal radiation. So
okay.
That's not necessarily well appreciated by everyone, because when we think about cooling our rooms, right, it's mostly done due to the air.
Right.
We mostly.
Then we should be wearing space blankets instead.
Well, people are doing that, right? So there's two angles on this. There's radiant cooling systems and heating systems for indoor spaces are definitely a prominent technology that a lot of people. It's old. It's an old technology, but it's finally gaining some traction in the market. And they're just they can be way more efficient because they don't need to actually cool or heat large volumes of air.
Mm-hmm.
They usually just cool or heat the walls or the surfaces around you, and that can keep you kind of comfortable. So
Yeah.
this is like this basic feature of nature. But what's different in what we're doing with radiative cooling is we're thinking about it outside facing the sky. And when you're looking up at the sky, you're basically looking towards space. And if we actually, if you take a temperature gun, which is what I'm showing right here, you can buy it at Home Depot for about $30. You point it up towards the sky, especially in relatively clear sky, California, you will usually read a much colder temperature than the actual air temperature because of this effect. And so if you want to get really technical, what you can do is you can actually plot as a function of the spectrum, the amount of heat that's going out from a surface upwards to the sky versus what the sky as a whole sends back to you.
Mm-hmm.
And so it's that net balance of what goes out versus what comes back in that tells you whether you can actually cool down below the air temperature. And so here what I'm showing is in blue, what's going out from a surface at 300 Kelvin, so that it's about 85 degrees Fahrenheit. And in orange is what the atmosphere is sending back to you. And the big difference is the atmosphere doesn't send everything back to you, because at these particular wavelengths between 8 and 13 microns, we have what we can call a window, like an atmospheric window to space. So there's different ways people describe this. This is, to my view, like the most accurate, also perhaps the most difficult to understand. But maybe one way people can appreciate this is like, if I look at these wavelengths right here, that's due to CO2, right? So that's the heat CO2 sends back to you. This is the ozone line, right? So this is ozone sending heat back to you. But at these wavelengths, the atmosphere sends very little back to you. So
Where's water?
water is continuum. It's actually, and so it'll kind of determine the height or the depth of this window right here. So the more humid it is, the more that goes up.
Just the whole kind of noise floor of the whole thing goes up.
Mm-hmm.
Okay.
So there's
So what's at 5 to 8? That's also CO2?
Don't quote me on that. It might be CO2, but there might be some other gases there as well.
Okay, cool.
So that's the basic technical reason this effect actually works really well. And so the net result then of this is that a surface that's facing upwards to the sky will be able to essentially send out more heat than it gets back from the sky, and therefore passively cool down below its surroundings. So it's, and again, I want to emphasize that the reason this works really well is what's outside our atmosphere is actually very cold, right? If we were not in space, you wouldn't be able to actually enable this effect. So as much as saying, we're sending heat to space is kind of a hokey thing, it's also kind of true in some deep sense, because it really is taking advantage of the fact that we are in a cosmos that is much colder than us here on the surface of the Earth. And so it's in that sense, if you want to get really fancy, you could say, well, you get heat from the sun. This is kind of the other direction. This is the heat we send out from the Earth to space. And so conceptually, from this kind of thermodynamics, like grand vision of the universe or whatever, this is like another renewable energy mechanism. So that's the grand kind of vision. But concretely, I think when we were working on this in 2012 and we learned everything I just told you, we were trying to figure out why we had never heard of this before. So, we thought we were reasonably knowledgeable. This is how come we never heard of it? Because it sounded really too good to be true. Like you just put something out there, it gets cold. That obviously had to have some value, right? That was the immediate kind of notion we had. And so there were many people that had published papers on this, especially in the 70s and 80s, but then it kind of, became a relatively quiet field. So as far as we could tell, there were only a handful of people that even were looking into this in the late 2000s and early 2010s. And we scratched our heads, and we came up with a couple of guesses. I think one of them was maybe it was just timing and kind of some things just line obscurity. It could be historical accident. But on the technical side, we thought there was another possibility, which is that this only really worked at night. This is called night sky cooling or nocturnal cooling, and that was not a great fit for cooling, because cooling needs are usually highest in the middle of the day when it's
Yeah.
hottest outside and the summer months. And the reason it didn't work in the summer and during the day is the sun. So when you're outside facing the sky on a hot summer's day, you are going to see the sun. And so if you absorb even a fraction of the sun's energy, it turns out you will completely counteract this cooling effect. So that was really the first and maybe still the core technical challenge in making this viable technology, which is, can you actually make materials that will not absorb the sun's energy? Ideally, they'll completely reflect it, right? It's a perfect mirror, but they'll continue to send heat out effectively at these infrared wavelengths out to the atmosphere into space. And if you could do that, in theory, you should be able to persist with this passive cooling effect that historically you could only see at night into the daytime as well. And that was the vision. That was the original kind of idea that we began working on actually back in 2012. And yeah.
So maybe just to put it simply for folks, as far as the like visible and near IR is concerned, it's, the goal is to be perfectly white, right?
Yep.
Or perfect mirror, perfectly reflective, and then at the same time be very highly emissive in this 10 to 13 micron window.
Exactly. So it's it's the opposite. If you've ever seen a solar water heater, it's kind of the opposite of what you want for a solar water heater, right? So in a solar water heater, you usually want it to absorb all the sun's energy and not emit its heat away, so it can get to the hottest temperature possible.
Yeah.
And so this is kind of the exact opposite. The only nuance is that the reason this works well is because of this property of our atmosphere. It lets out some of the heat.
Right.
And that's what allows you to cool down below your surroundings.
Cool.
So yeah, I mean, this was an interesting challenge, and it was kind of totally right up our alley, which was thinking about from an optics point of view, how can you make something that could give us this desired set of properties? And so, we're like, let's do it. Let's figure out how to do this. I'll just get right to the experiment and the details, but I'll also explain maybe a little bit about how this all came to be from a financial point of view, which is that we, at the point we started realizing these things, we pitched ARPA-E, which is an agency in the Department of Energy, and they had every few years they have an open funding call, and we sent in a white paper, and we were encouraged to submit a full proposal. We were very fortunate to get funding for it at that time, because I think if we hadn't gotten funding at that time, maybe we would have written a little theoretical paper and I would have moved on to do something else with my life. So it kind of definitely changed the trajectory of my life a bit. But we probably got one of the smallest grants they had ever given till that time. So it was only about $300,000, which for ARPA-E is relatively small.
Yeah.
Later on, I would discover part of the reason was that they were. I think they had never received a proposal on anything related to this topic before, and I think many of them hadn't even heard of it, which surprised them because they're all.
So they were worried this was sort of a cold fusion kind of proposal, maybe. So
they're like, well, it's a small amount of money. We should give it to them to figure it out. So yeah, there was definitely skepticism. Apparently, like, Steve Chu heard about it and was like, I'm not sure that doesn't sound right, but let's see if they can try it.
Yeah.
And so that was the reaction, right? A lot of people when they first hear about it, they're like, that doesn't make any sense. And these are like very highly trained physicists and engineers, people think about energy.
Yeah. Well, I'll tell you, when I told my neighbor about it, who's an atmospheric scientist at JPL, he literally went like this. So I think there are definitely a lot of people who appreciate it, but I think that's really important, and to remind folks, right, that like, what's the saying? It's like every really good idea is like ridiculed and at first, and then becomes completely obvious later, right?
Well, I mean, I think we had a few things going for us, right? It was, people had published papers on this, right? So there
Hmm.
was some precedent. There were, the people and the people that actually understood this were climate scientists and atmospheric scientists and
Hmm.
your local meteorologist
Yeah,
actually understands this probably really well. So there, we were not coming completely out of the blue. I think that's also an important thing to point out, is that, the case we made to them was, look, there's this technology that had been investigated in the past, never really found traction, but we've had a couple of decades of work happening in this other field in optical materials and photonics that has given us a lot of capabilities we didn't used to have in the past. So let's bring
yeah,
those ideas into this technological context and see if we can enable something new. And
right.
so it in retrospect, when I say it now, it's I think a pretty compelling story, right? It's that it's not that we're completely telling you something you've never heard of before. The reason you haven't heard of it before is not that people hadn't worked on it; it's just a little obscure.
Yeah.
There was scientific precedent. There's lots of papers, and some people in the
Well,
buildings
and
world had implemented it even. So
yeah, and I guess I'll apologize for if I'm getting it wrong, but I was sort of maybe what I haven't quite revealed to the audience is um, I was somewhat able to watch some of this in real time because I was also working on nanophotonics and
yeah,
energy things at the same time. So I'm actually, could you just help me with the timeline? Because I'm remembering there was I'm remembering an MRS with a presentation and maybe a paper that was like pure FDTD kind of simulation, and it was some like many dozens of layer metamaterial with three-dimensional refractory metal photonic crystals and all these things. So was that simulation, was that computational result sort of part of the, like, was that done before ARPA-E was like, yeah, okay, like you showed it in simulation? I just want to understand the like how
yeah. So
de-risked it
we
was before this experiment.
Yeah, I mean, and the context here is that I was until that point a theory and simulation person entirely.
Uh-huh.
So
Okay.
I worked in a research group that primarily did more theoretical things and
Yeah.
very rarely did experiments, with some exceptions. And so yeah, our instinct was to write it up as a paper, and it was a good paper. I think it had some interesting points to make. But it was primarily the data we put into that RPE proposal, actually.
Oh, so that the
So
simulation was the input that kind of said, hey, this is possible.
right.
Cool.
And so I think at that point, and perhaps this is purely because we were biased from our background in the field we were in, which is we tried to throw like everything we had at our disposal. We went like really heavy duty
Oh
into
yeah,
the
I remember there was lots of
anti-proliferation.
tungsten in there and gallium
Well,
arsenide.
no, this one didn't have tungsten. It had
Oh,
silicon carbide.
oh, silicon carbide. Okay, all right.
But yeah, I think it was uh, perfectly fine as an academic paper. But ARPA-E did one thing which was, I think, ultimately a good thing. They only give us money for 1 year,
Okay.
so we had to demonstrate that we could actually do this at a meaningful scale. So something like this big.
Yeah.
Um, in a year, which
Okay.
is not a lot of time.
No,
Uh,
it's not.
yeah. So and so when I got to working on the topic, then I realized I wasn't going to be able to make that original design fast enough, and it was just going to be too complicated. And then I stepped back and I realized you probably don't need to go that far, like that.
Mm-hmm.
This was probably overkill. And the simplest thing you can do in nanophotonics, if you want to give that label to it, the simplest thing you can do is just thin film coatings, right? Optical interference coatings of various kinds. They've been around for a very long time.
Mm-hmm.
And so that was the I think kind of an important transition point where not only because of time pressures, but also because I was really starting to think about its viability as a practical technology, I realized the obvious thing to do would be to be able to show this just using traditional thin film coating approach, because this was a very established manufacturing technology.
Yeah.
Right? This has been around for decades. Um, later on, I would get to visit like a factory that made low emissivity window coatings which get done, like they do 1,000,000 square meters a year. And these are, 11 layers, 10 layers, I don't know the exact number, but with, tens of nanometers precision, they're doing these over 1,000,000 square meters a year, right? At super cheap costs. So that realizing both the time constraint and the reality of actually making something into a potentially commercially reasonable technology led me down a very different path. So the ultimate design we came up with is just it involved a couple of materials, and I don't want to fixate on the specific choice of materials, because I think people kept on thinking this was just the only thing that would work, which led to some very strange interpretations of this. But it was just that original thing was just putting, the first thing you need to do for a good solar reflector is the cheapest thing you can do is put a metallic mirror. So a silvered surface, silver is a very good reflector of sunlight. So you start with that, but silver is not good enough for this purpose. So you add additional dielectric layers, alternating high and low index, which is again an old idea. But I think what is kind of interesting here is we also needed to play with that longer wavelength regime. And so it was partly just using some algorithmic approaches to try and optimize for it. But we got a relatively odd design where you had some layers that were super thick and some that were extremely thin. And they basically targeted different parts of the spectrum to maximize the reflection and also give you this infrared emissivity. Actually early on, we just sent these out to vendors. So that's the great thing in the space. There are lots of vendors. You give them a design, you tell them what material, and they'll make it for you, and they'll send it back to you. So this is just like e-beam evaporation, right? So a very traditional process. And so you get the design back. What do you do? Well, within about 6 months or 7 months of the project start, I already had this wafer that you're looking at, this little circular disc right here. And then we realized the only way to actually test this was to put it outside. There was no simulator for the sky. And as far as I can tell, no one has ever built one. So, the simplest way to test it was to actually go on a roof and put it up outside. But then very quickly, I realized we had a problem, which is that if this thing was cold, but it was on a warm roof, everything on the roof was trying to heat it up. And pretty much every natural material heats up under the sun enough that it'll start heating this thing up. So oddly enough, we spent about a month or two just trying to figure out how you could even test this, like how you can design an experimental like rig to test this. And it's only because we were doing this over small areas, right? If you can do this over a large enough area, you don't have to worry about these challenges. So it's one of these weird quirks of trying to do a very small experiment first time around. And then it was really cool, right? You put it outside, you face the sky, and the first time I put this thing, immediately the temperature reading on it started dropping, even though the sun was shining on it. And it dropped as soon as I had something covering it. I took off the cover, and then I was looking at the temperature, and it started immediately dropping. And it was starting to drop below the air temperature, and you're like, "Whoa, it works."
Wow,
that's pretty much it. It was as simple as that. And so you can touch it, and you're like, "Oh, it's cold." So it's a dead simple experiment, right? It's I never claimed to be an experimentalist. I just kind of pretend to be one. So and that we had to do a lot of follow-ups and make sure we were not making some false readings and this and that. But that was it, right? So that was kind of like the key result. This is the data from the paper. We managed to get it into a fancy journal. The really counterintuitive thing is, again, that makes this a really interesting capability is that even though the sun is shining on it, if I expose it to the sky and the sun, it will cool down. And so if I were to then bring it into the shade, it'll actually warm up. And that's because you're blocking access to the sky. So it's it's a very nice story, right? It's a very counterintuitive thing. And so from an academic point of view, excellent story. And so, but this kind of brings the story to like this interesting question, which is we had this $300,000, right? So what next? And we'd proven it out. So ARPA-E is now interested. And obviously with what we had so far, that wasn't enough to immediately commercialize it because there was no conception of what a product could be, where it could actually fit as an energy technology. And so we sold ARPA-E on a bigger vision. And we eventually ended up getting a total of about $3 million to develop this over many years. And the vision was, one, we need to scale up the materials themselves. So that's part of the challenge. But the other was to actually prove they're being utilized in a way that showed energy savings, right? That we were able to connect the dollars saved in terms of either electricity offset or some other metric with the technology directly. So and so we spent a lot of time in that early years. ARPA-E actually made us do the I-Core program before they would actually, or as a condition of getting the money, which I believe we may have been the first team they ever did that to.
Well, and now they have their own DOE version of iCore, right?
Yeah, I think it's called
Yeah,
LabCore or something.
LabCore, yeah.
Yeah.
For the
So,
national,
and so for those of you that don't know, the I-Core program, funnily enough, it was based on a Stanford class that I had actually taken in 2012. There's a guy named Steve Blank who has this whole lean startup, who's been a big evangelist for this lean startup, lean launchpad philosophy. And me and some colleague, PhD classmates of mine, we actually did the whole lean startup thing on using, we call the company Dental Optics. We were actually trying to figure out some way to use light to improve dentistry.
cool.
So originally it was about lighting the inside of the mouth better so that dentists didn't have to wear a lamp. And then we discovered that wasn't going to work. So the reason we discovered it wasn't going to work then, and the same philosophy of the I-Core program, is this whole idea that before you invest a lot of time and money, you spend a lot of time talking to potential users and customers of your technology. And so, both for that class-based scenario where we ended up knocking on every dentist door in Palo Alto, to this I-Core program, we ended up talking to on the order of like 100, 200 different people connected with the relevant ecosystem. So for radiative cooling, that meant talking to people that ran facilities for all kinds of buildings, HVAC engineers, kind of VP level people that made purchasing decisions at big companies and chains. So it was super fascinating for me because I, at that point, knew nothing about this industry, about air conditioning, HVAC. I vaguely knew how they worked, but that's about it, right? So this was, I think, a super important thing. And it happened while we were still at the university setting and before we actually solved some additional technical problems, right? It was this very, at the time I thought it was actually too early to do this because I was like, look, we don't even know what the numbers are. Like, I don't know how much this is going to cost. I don't even know what the exact performance is that we can hit realistically, but we just kind of made it up. We gave them ballparks. We looked at like, it turns out you can do a lot really early on. Like as long as you have some sense of what your technical capability might be.
Right.
And so,
I love it. And I think the way that I kind of conceptualized it after learning this methodology myself was, oh, this is just the scientific method now applied to people and markets. And and Steve Blank's whole thing is, there's no truth inside your building, right? Like you got to get out of the building. And so I think that's a really useful framing, especially for inventors and scientists who quickly fall in love with the invention and, oh, if it only did these three things that are next on my list, then everyone in the world will appreciate my thing. But I love that Steve kind of forces people to say, okay, take that same scientific rigor and go say, hey, here's my hypothesis. Whole Foods is going to love this thing, and then go ask them. And what would be required to actually put it on the roof at Whole Foods, and right.
Yeah. I mean, so the joke would be that with Steve Black teaching our class, we pretty much every class you could count on him saying "get out of the building" at least a few times.
Oh, really? Yeah.
But it was so. I mean, I think that's actually a little bit of important context, right? Like I didn't come into all of this being completely naive about starting a company or anything like that, or about that aspect of it.
Hmm.
It's not that I had a ton of experience necessarily, but I'd worked in industry a little. Weirdly enough, I was briefly part of the very first Y Combinator class in 2005, but our
Wow.
company didn't make it for various reasons. But we were at least accepted into it back then. And so I had some inkling that I was interested in this kind of stuff. And honestly, being at Stanford was a huge help because we had the ability to take a class with people like Steve Lang.
Yeah.
And so I definitely did a lot of things besides research as a PhD student.
Yeah.
Something which I do not necessarily tell all my PhD students. But I think that was actually really important because when I came into this, I think I wasn't totally naive. I mean, I still underestimated, I think, how hard it would be,
Yeah.
even though I knew it was going to be hard, and I'd seen all these clean tech startups, fold right in the early 2010s. A lot of the solar companies were not going forward, so it was definitely an interesting time. But ARPA-E, yeah, they forced us to do this thing, which ended up being very valuable. But it also, we had a choice, I think, to pull the trigger on starting the company sooner rather than later. But we realized we were still maybe a little too early, and so we spent, a couple of years, like 2014 in particular, and then 2015. Because that's when our ARPA funding was there. We essentially did a lot of that scale up, right? We not in a true company sense, but in at least taking it to a higher fidelity prototype that is more representative of what a product might be, and it also gave us kind of a bit of breathing room and time to for me, one of the most important things was finding a co-founder, or a potential co-founder, and so. The person I found is now the CEO of Skyco. His name is Eli Goldstein. And so Eli was finishing up his PhD in mechanical engineering at Stanford. We'd met before. And he was one of the few people I've ever met who had some experience with HVAC systems. And he is, a total pro with heat transfer. And so it made sense, certainly on the technical side. And I think he was really interested and passionate about the technology from the beginning. And so he joined, and the two of us worked essentially as postdocs for like a year or two. While we were figuring out the technology, we were also trying to then figure out, what would the company be, right? What's the business case? What is the go-to-market strategy? What's the story, right? That we can sell investors on, potential customers on, like what is all of that? And so the company itself, we officially started in 2016. It was only towards the middle of 2016 that we really left Stanford for real. And part of that is, I think, as first-time founders, figuring out a lot of stuff, right? And so it was, the big, other useful thing we were able to do was some of the ARPA-E funding was, the company essentially, we realized a lot of the final milestones of the ARPA-E project we couldn't really do at Stanford. They were going to demand, it just didn't make sense. Like it was about really doing a larger scale demonstration and hooking this up to cooling systems. And so that made much more sense as a company. And so with everyone on board, including ARPA-E and Stanford, we started the company, licensed the IP, and were able to kind of allocate the last bit of ARPA-E funding towards the company. So in addition to a very small amount of seed money we were able to raise from friends and family, we had this ARPA-E funding, right? And then and we were then also able to separately apply for an NSF SBIR, which is a small business grant. And so those things kind of allowed us to operate in 2017 and 2018 without raising really any significant private capital.
Yeah.
And so what that allowed us to do was really refine a vision for the technology. And so stepping back, you can think of this technology being used a lot of different ways. One way is you can just put it on the roof of a building, right? So, but we realized if you did that, there's some value, but you weren't really maximally extracting the potential energy savings benefit out of the material itself, right, and the surface. And we realized one of the biggest benefits we could get out of the system is if we hook this up to a cooling system and directly offset its energy use. That's where we would see sort of the maximum kilowatt hours of electricity saved per square meter of panel. Because we realized very quickly that's where, that's what customers care about, right? They want to know what their payback period is, what the IRR is, if they're actually, the internal rate of return, if they're actually investing on it in a project. And so I think that, that interaction with customers really clarified that point for us, that this was really for our company and for a business, in terms of a business case, this is what made the most sense, because then we could actually sell discrete products and systems that would integrate directly with the HVAC side, and we could prove electricity savings to customers right off the bat, instead of, you sell a material, it goes on someone's roof, and then, someone has to do some analysis, and that just seemed like it would be a much harder problem to solve when you were starting out as a new startup. It's not to say that that's not a potential market for the company in the future. It's just when you're starting out as a startup, you really need to figure out that highest value, like where you can really provide highest value to someone. And the vision then was really, it comes down to how an actual cooling system works, right? There's a cold side, which we're all familiar with. It's when you open your refrigerator door or in a supermarket, you open the case, that's what's keeping stuff cold. But the way it's keeping stuff cold is it's actually taking heat away, compressing that refrigerant, and then having that refrigerant condense on the rooftop, typically, of the building, right? And so the condenser usually looks something like this if it's an air-cooled condenser. And depending on the temperature of the air, that compressor is going to work harder or less hard, right? So if it's a hot day, your refrigeration system is going to have to do more work to do cooling. Makes sense intuitively. The reason it has to do more work is that condenser has to be at a higher pressure and therefore a higher temperature. And so our vision was really to be able to hook in to that component, the condenser, and right after the condenser of any vapor compression system with a heat exchanger, and then run our panels, an early version of which you're seeing in that previous picture, as a secondary cooling loop. And so the benefit, therefore, that you get is that this is an add-on, right? So one of the things we discovered very early on is that this is, by and large, a relatively conservative industry, like air conditioning, refrigeration. New technologies take a long time to get into the market, which is a problem if you're a startup. And so I think if you're proposing, and the reason new technologies have a hard time is often new technologies are rethinking the entire system. And that's a big ask for people, especially when they're doing mission critical things like keeping $1 million worth of frozen stuff safe, right, in a difficult supermarket. That's the risk of failure is just way too high. So people are super conservative about this. But if you propose it as an add-on, which in the worst case, the worst thing it'll do is return your system to its original level of performance, people are much more willing to consider it, right? So even, and this is an interesting lesson, right? This is not necessarily the way you're going to save the most energy using radiative cooling. There are definitely ways where you could use these radiative cooling panels as the entire condenser of the system, or to radically reimagine a building's cooling system. And you might be able to get to 80% savings, come and radically change, right, the way we do cooling. But no one's going to buy that, at least not initially. Especially for something that is so strange and unfamiliar to people. right? We were coming early on, we were coming, we're like, hey, we're postdocs at Stanford with this fancy material and a panel we put on your roof, and some mechanical engineer or some HVAC tech is like, what on earth are you talking about? Like, what is this? Sounds like, and to be honest, there's a lot of weird, possibly, fake stuff that gets sold in the sector. So
Yeah.
so people naturally have their guard up, right? So I think learning how to sell to this sector it took a while, and all credit to Eli and the team. Now they've, I think, really understood what the value proposition is that people care about. And even if, and one of the biggest things we learned was that even a 10 or 15% energy efficiency gain was considered huge to a lot of these people. In fact, they thought that was actually fake. Like, they didn't
They thought you
believe
were lying.
they thought that was lying, because most of the products that were getting sold in the space were still in the 1 to 5% efficiency gain space, right? So, and that's because it's a hard problem. It's just a really difficult, thing you're trying to do. You're trying to move heat from one place to the other. The systems have been optimized pretty well over 100 years. So if you're coming in, like, you're and it's obviously competitive for us, but there was skepticism on that. We were originally worried that we weren't going to be able to show like a 50% energy savings, right? And often investors want that, right? Investors are like, why aren't you going after 50%? We're like, well, it turns out 15% is a lot, and in fact a little unbelievable for our customers.
Yeah.
And so it's like this really,
they'd be offended if we offered 50.
it's different worlds, right? Like, a lot of the people that are traditionally thinking about renewable energy and climate things are thinking about big step change solutions, whereas the customers are, not thinking in the same ways. They're often more focused on their bottom line, and they'd like to do something good from a sustainability point of view, but for them 10% is huge. And so that was very encouraging for us, like, because we realized we could, and so this, what I'm showing you here, this vision, this add-on thing took years to arrive at, right? It wasn't a fully formed idea back in 2014. So and so in 2018 we did our first field trial. We actually published the data, and I think publishing was actually important for us, given how new and this was, and how people would be naturally skeptical. And we were able to show up to about 15% electricity savings using this approach. And I mean, I love this picture because this was done over the summer in 2017, and this is out in a facility called PVUSA in Davis. Right outside UC Davis. It's a very old PV testing facility. And what was really nice is we didn't need to do any special permitting to do this facility. It was allowed to do experimental tests like what we were doing. So we essentially bought off-the-shelf freezers, rented a container, and air conditioned it, which is what you're looking at on the left right there.
Oh, got it.
And so that's an off-the-shelf air conditioning unit. Our panels were sitting there, hooked up to these air conditioners. There were like squirrels everywhere. It was and these like little biting insects. Like, it was a lot of in the field work.
Yeah, and then you had to live under that pop-up instead of inside the container to not buy it.
We did not live. But and so this was, by the way, the last phase of the RPE project, right? So we wanted to actually show model scale demonstration of radiative cooling.
Wow.
And so, this is about then 5 years from theoretical conception, the thing you saw at MRS, to something that's, a 10 square meter scale, right? Yeah. And so this provided us the first real concrete data that we could actually improve the efficiency, you could save electricity in these systems. Of course, the problem is, this is not an actual customer, right? So I think the next big step that Eli and the team have really been leading is getting this from that field demo to something that looks more like a product. And so this is our first generation product hooked up to a real customer system. So this is a grocery outlet supermarket. It was installed in 2019, at the end of 2019 in Stockton, California. And so this is the world's first radiatively cooled supermarket.
Wow, do they put that on the front?
I don't think they have, but they've been very kind in that they've allowed reporters and others to talk
Go on
about it,
their roof.
and so shared the information. So, and it's really interesting. I think they like the energy savings. I'm not, it was. I think it's still a confusing concept from a technical point of view to a lot of folks in the HVAC space,
Yeah.
because it is very different way of thinking about the cooling problem.
Yeah.
Everyone's used to condensers. This is a larger area thing. And so, you've got a fluid loop running through these panels, and then they're returned back to a heat exchanger that interacts with the refrigerant line. And a lot of things we've done to simplify our lives. We use solar racking, so off-the-shelf solar racking that's already certified. We're basically trying to simplify the process and get to market as quickly as possible, even in this industry and domain that is challenging in that regard.
Yeah.
So
Cool.
this was a huge milestone. And just to share some data, this is all public on our company's website, so nothing confidential here. But essentially, we to prove this out, and we work with a third party here, but to do a lot of this validation. But we essentially the panels are either turned on or off, and then over lots of different days we look at the energy use, right, as a function of ambient temperature. Generally speaking, your refrigeration system uses more energy when it's hotter outside. But what we're able to show is that whenever our system is on average, you're going to save a lot of electricity. So it ends up saving about 100 kWh a day on average for the supermarket. And so that corresponds to, assuming 15 cents kilowatt hour, about $5,800 in energy savings. And so this was for us super encouraging, because this was really getting at that value proposition, right? We were now finally on a customer's roof. It took us all the way till 2019 to get to this point, but we were on a customer's roof. We know how much these things cost. We know how much energy we're saving, and now we can prove that payback period, the ROI that people want.
Yeah, that's amazing.
And so, yeah, this was another case study. It was a gas station in Sacramento. This was actually our first installation. It was a bit smaller. It was done in January of 2019. And this was sponsored by the Sacramento Municipal Utility District. And this was showing a 15% reduction in daily kWh of a cooler freezer system in a smaller convenience store. And again, you can kind of compare the baseline system with the savings you can get. So, again, early on, we also realized as partners, utilities would be really important working in the energy space. And in terms of other non-dilutive sources of funding, we were also very fortunate to receive a large grant from the California Energy Commission.
Yeah.
That is supporting some of the larger installations with first pilot deployments with customers. And so, in addition to private funding that we have raised since, I think those non-dilutive sources of capital have been super important.
Yeah. Yeah, that's awesome.
And this is kind of another example of condenser usage as well, just to prove the point that you can get up to 25% reduction in kWh.
So this goes straight into the ice machine?
It basically, instead of using a traditional condenser, we have a heat exchanger which serves as a condenser, and that heat exchanger is entirely cooled by our panels.
Got it.
So there's no air-cooled system. And so here the energy savings are larger because you're reducing the overall condenser temperature significantly.
Right. So can I ask a question? So the electricity savings piece is obvious, and what you quantified here is the amount of HFC leakage proportional to the work, so to speak, that the system has to do? So are you also stopping leaks by not having the system overclock itself, for lack of a better word?
That's actually a great question. To be honest, I hadn't thought about it. So that's really clever. I think we should look into it, because you're right. In principle, well, so leakage is a complicated thing. I think, and this is actually something the EPA studied quite a bit, from what I can tell. It is most likely occurring at some joints and some interfaces, usually where a pipe has been brazed to something or whatever, another heat exchanger. So I think the short answer is I would expect so, just because you're moving more refrigerant around. So there's
right. So if it's proportional to the flux of
I would
refrigerant.
I
And
would get, yeah, that's a good guess. We'd have to look and see about the data. It is actually very tricky to measure it, like, and prove it
uh-huh,
concretely, but it would be super interesting if someone has already studied this to be able to point to that. I think that would be really interesting.
yeah,
The other angle for us is hooking these panels up to these next generation refrigeration systems. So like CO2 based refrigeration, or
yeah,
there's propane for smaller systems, ammonia for like cold chain systems. So
wow,
I think yeah, I mean, it's really interesting. Different people respond to different angles, right? For some folks, it's about dollars saved. For a lot of others, it's about the sustainability or carbon emission side. And
yeah,
um, you know, I'm personally super motivated by the fact that uh, I was able to make something that is, starting to save emissions, even if there were a lot of input emissions to get to the process, in the R&D
yeah,
process. The more panels we make, the more we deploy, I think the better it's going to be. But I think for people that you sell it in different ways, right? You find what appeals to different ways, but the net result is the same, right? The net, there's you'd be surprised. Like, there are, I remember meeting some folks early on in the customer interview process, who openly said they weren't really sure about the climate change thing. And we're like,
yeah,
okay, yeah, so I mean, part of this is like, the it's kind of like a cultural thing. The type of folks that tend to work in HVAC are very removed historically from the climate and energy space, particularly more of the people that actually work on the systems, the techs, the
right,
staff. Um, Demographically, from a cultural point of view, are not likely to be super, climate hawk, green, green forward people, right? So,
mm-hmm,
but that doesn't mean they don't appreciate other aspects of the technology, right? So you
right.
you kind of, yeah, and I think there's a lesson there, at least for me. Like, it's very instructive, right? But you can
Sure,
still get
and you don't
benefit.
need. I think the thing that's valuable about it is like uh, debating with this person about whether or not climate change is real is ultimately like not productive for you to
No,
solve the problem,
I
or for for the company to sell a system and actually make an impact. It's almost like I just that ability to connect with different people on different levels is,
yeah,
regardless of politics or education or you know uh, socioeconomic kind of background.
for sure. And some customers, but some customers, for example, bigger chains, or like, bigger corporate customers, are obviously, they have sustainability goals, right? They
Yeah,
are, that's a different ball game. So for them, they will actually care about the emissions you're offsetting. So um, and I think this is likely true for a lot of people in the energy space, right? You are a lot of startups in the space that you can't rely purely on, um, at least, in many cases. Perhaps some are able to do this, but at least for our case in this industry, I think it would not have been made sense for us to purely market or pitch the technology purely on the fact that it was green or renewable.
yeah,
And in fact, doing that too much can actually hurt you. So I think it's an interesting lesson, because um, perhaps for a lot of technologies.
yeah. So speaking of lessons from other technologies, we've talked a little bit about RPE being the sort of the first investor, so to speak. and
Mhm.
you use the word non-dilutive funding, which obviously, um, in our world of kind of deep tech, I think a lot of people will understand. But I think for those seeing this that maybe don't understand the like dilutive, non-dilutive, and also maybe the like why it's so critical to be thinking about non-dilutive grant sources of funding. I guess what advice would you have for uh, the next PhD student who who invents something
Yeah.
their, in their group in terms of let's say the financing side of, taking it, the idea to reality.
Yeah. I guess, I think there's more you, there's more sources of funding out there than you think. I think part of it is honestly just searching a lot, and finding funding calls can be harder than you think as well, because they're often hidden away on different sites. But every government agency has some kind of SBIR program. So if
Mm-hmm.
you likely with your idea connect with some aspects of so this is a small business investment and research, or I forget the exact
Innovation and
innovation and research.
research, I think. Yeah.
Yeah, a grant. And so the most well-known one is likely the NSF SBIR, and they've done a great job in recent years, I think, really making, I think, the process a little easier, perhaps, but also explaining it to first-time applicants. And
Yeah.
as far as I can tell, they encourage first-time applicants as well, especially if you're coming out of your PhD or postdoc, or you have some R&D goal. And so, uh, you know, those those sources of funding are great, but I think you eh, you know I think it helps to sooner rather than later get a little uncomfortable and move out of research mode and
Yeah.
being a researcher, and really um, part of it is when you have to make payroll and you have a bank account.
Yeah. So maybe that's another question is, I often will, in my community and our community, I think both of us could probably think of, I don't know, 5 to 10 people that maybe have too many grants and not that are not academics, right? They are a startup, but
Yeah.
they kind of end up in that, the like, oh, I got to get the next SBR and the next SBR and win the next pitch competition. And so that's another question I have is, at what point is enough and it's time to be a real business?
So I mean that's a great question. I don't know that there's a universal answer to this, right? I actually think it comes down to what the grant is funding you for. Like, what are the
Uh-huh.
milestones? What are the expectations? So I think if you go chasing after the grants and write to them, but that actually moves you away from your pathway to becoming a business, that's probably not great. But if it can align with your goals, right?
Yeah.
Like for instance, for us, the grant funding actually, supported pilots, right? Getting it into the hands of customers, making it more likely for certain customer segments to, install it because it was subsidized, or not
Hmm.
subsidized, but like we were able to essentially give it at cost, or lower. Like those kinds of things are
Sure.
very valuable because for us, that is getting us to certain milestones. It doesn't preclude us from also selling the system and stress testing those aspects of the business.
Right.
But it also kind of facilitates growth, right? It
Yeah.
facilitates the business development strategy. But again, other technologies just need a lot more like R&D, right? That take longer. In our case, part of the reason I would say our story is relatively quick because we were able to leverage some existing contract manufacturing capabilities and external
Yeah.
vendors, right? We didn't have to build up our own giant manufacturing facility. We don't have one. We are not, so we are not in the same ballgame as I think some folks that are
Hmm.
in the SBR space. But I think where the SBR thing can lead you astray is that if you have a particular vision and goal in mind, but the funding calls are very specific and require you to deviate from that strongly, you should think carefully about where that's leading, the company.
Yeah. Yeah, that's great advice. And I guess I think I'm also biased by saying this is a good commercial for NSF SBR because they're really amazing. I'll just say to folks out there that in my numerous experiences with them, they have been insanely supportive of making sure that if the proposal you wrote is no longer in line with the business objectives, they'll just, they're very supportive of letting you change the milestones to realign with the business. And I think that's a good, let's say, I don't know, question to really ask yourself, right? Like, am I just throwing my name in the hat because it would be nice to get another 150, 200K non-dilutive, or maybe $1 million for the phase twos, right? Or
Yeah.
is this really critical path with the business that we're trying to build? And actually, along those lines, has the quote unquote sort of like brand value or like seal of approval of an RPE, of an NSF, of a CEC, is that useful in the energy space to be able to say, hey, this is, stamped by the United States Department of Energy?
It is to some extent. I
Uh-huh.
think it's unclear to me how much it ultimately matters to our customers, as far as I can tell. It might to some extent.
15% is 15%.
Right. So it's the proof is in the pudding for them. Like, I mean, I'm pretty sure many of these customers have no idea what ARPA is, right? They know
Right.
about the Department of Energy, but
Yeah.
they probably think about it in terms of standards or
Right.
regulations or something
Okay.
like that. CEC, perhaps. So it really depends. So certain customers, I think, will know about it. Certain, like,
Yeah.
you know, big companies with R&D departments that send people to RPE conferences will will know about it. But I'm fairly certain that the grocery outlet owner that we met did not. I'm not sure that mattered too much, but um, it can provide a lot of validation with investors for sure. I think to distinguish yourself from everyone else, it doesn't mean you're going to get money, but I think it can certainly help.
Right. Okay. That's fantastic. I guess any other advice that you'd have for deep tech entrepreneurs or folks thinking about making that jump from PhD to entrepreneur, or PhD to CEO?
Yeah. Well, it's it takes longer than you expect in some sense. Meaning often you're overly optimistic, I think. But the at some point, if you've never done this before, I think it should feel maybe a little scary or uncomfortable. Because I think when you're at an institution, I think there's kind of like a safety net, and
Hmm.
and I say this now as a faculty member at an institution, but you have like a backstop. It's not perfect, but there's there's some security, especially if you've been there for a while already as a PhD student. And we, I think, struggled with this question about when to start the company and when to leave Stanford. I don't know, we made some choices. I don't know that if they were the right ones or not. So I can't speak to everyone's experience. But it seems to me that depending on what you're working on, there is kind of like probably a sweet spot for when you should leave. For certain technologies, you may actually not want to start it right away or not be fully operational right away, because it's maybe not your pitch isn't quite there. You don't have enough data necessarily to get everything you want. Although obviously with Cyclotron Road and related programs around the country, I think that provides a really nice alternative where you can
Yeah.
operate as a company and continue that basic R&D. But if you're still in a university setting, I think it's important to think carefully about what it is you need to do, how long you think it will take, how long, be real with yourself there. But it's also important to, at some point you have to take the leap
Yeah.
and kick yourself out and go through the mechanics of, filing for incorporation, getting an accountant, doing all that stuff. And for people, it is getting that first SBIR that does that, right?
Yeah, because you
Um,
can't accept it as a postdoc.
exactly. So I think that the SBIR does a good job in forcing people in that regard. So, but it's I think it's a tricky thing, and I've seen people, you know, on both sides of it. Some stays too long, some that maybe went out a little too early and raised some private money, but it was probably not the best use of it or best time to raise it. So it's a tricky question, and I'm really glad, that cyclotron road exists. And in a I probably should have participated in that very first class, or tried applied at least, which is a whole nother story of why my thinking around it at the time. But I think it would have it provides that, it tries to provide that balance, right? It's really good.
Yeah.
Again, now we're providing a pitch for a section.
Hey, that's I've been doing a lot of that for the last 5 years, and yeah, and
but I
I
mean,
can safely say that I wouldn't have started a company without them, right? And
but even if you're at a university, right, it's possible to do these things. Like even if
yeah,
you don't have the cyclotron, it is possible. It's harder. Maybe you don't have the night network, right, resources. I agree. These are challenging things, but um, you know, I think figuring out like where, when, how to do that. And then, there's also always tricky questions about like being a founder, someone full-time versus part-time. There are all these things that emerge for research-driven startups.
yeah,
In my own case, I initially started out kind of in the CEO role for a couple of years. And now, I'm not full-time in the company. I work part-time primarily on certain technical problems, but Eli took over as CEO. And I think that was partly a personal choice about what I wanted to do, what I enjoyed about the job, what I didn't, and where I thought my strengths lay. Again, I think it it will really depend on the individual, right, and
yeah.
what their own personal motivations are. So, um, no perfect answer for everyone, but um, I I think I will say academics are probably more likely to stay a little too long. So if the bias should be to kick yourself out
To
earlier.
kick yourself out of the nest. That's amazing. So hey, I want to be respectful of your time, and I really appreciate all of the nuggets here, and it's just, to me, like I said, it's kind of a smack your forehead invention here. But I guess the last question that I want to ask you before we wrap up is really connected to that co-founding piece and that people piece. And I'm curious what advice you might have for young co-founding teams in terms of the interpersonal dynamics of of what it means to be a co-founder, or setting really clear expectations with each other, and maybe with your PI, or with there's all these kind of complications, and it's a natural let's say shift in the relationship dynamics, and so I'm just curious if you have any advice. And we don't need you to go into any drama or anything like that, and I'm not
Yeah.
suggesting there is any, but just how do you really what's your advice for like setting really good expectations with co-founders?
So I mean, fortunately, in our case, I don't think there was any drama as far as I remember,
That's amazing.
yeah, which was good. And I think but co-founder relationships, and others have written about this in probably more eloquent or detailed terms than me, but I think they're tricky, and they're kind of marriages of a sort, in that you are likely working with this person for many years, often decades, and um, I think figuring out a communication style that works is very important. Now, the tricky thing, I guess, often is when there's a PI involved, who is, and figuring out their role, whether they're going to be full time or not. And it's, the general rule of thumb is, I think, you need people full time on it,
Hmm.
at least for some amount of time early on, because the co-founders will work harder and have to figure out things that, and in those early days, that are just really hard problems that will require a complete focus. um, and so Which isn't to say that people working on it in some part-time capacity aren't valuable and important in a different way, but it's the being able to find some core group of people, usually 2 or 3 is the largest number I guess people recommend, but in that co-founding team that are full-time, right? They're full-time in on it, is I think the most important thing you can find. Now, what is also true is, like, for example, in my case, that at some point you may realize, while you do enjoy a lot of this may not be what you want to continue doing full time. I think finding pathways for that is also okay. That often happens.
Yeah.
And in my case, I've been very fortunate in that Eli has been great. He's been an amazing CEO and has like really driven the company forward. And on the technical side, it became very much about HVAC systems away from my core area on the optics side. So I'm able to contribute to on the technical from my technical side whenever it's needed. So I still am in on lots of meetings and stuff, but I'm also very confident in the team that is now in place. And so but I don't know how typical that is, but I think it's not a bad thing either, right? Because it's not, as you're developing the company, you've got to remember people may have different interests, and they may discover things about how much they like aspects of the job or they don't as they're going through it. And being able to kind of accommodate that in a graceful way that's also fair to everyone, from things like equity and all that, is, I think, super important.
Yeah.
And part of that, involves just having the right kind of people, like people you can trust and that are ultimately like fair and decent people. And so, I mean, in our case, Eli and I worked together for a couple of years before we even started the company, right? So, I think early on when I first met him, I was like, I think this could be, a company or something, and he was interested in that. But
Yeah.
we knew it from the beginning, but we also had time before we even founded anything.
To figure
So,
it out. Yeah.
yeah.
That's amazing. Awesome. Well, thank you so much for your time today. I know I learned a lot, and I'm sure that this is going to be super useful to many other deep tech founders in the future. So, yeah, I think with that, we'll thank you. I guess one final super last question is, where can folks find you as a, PI and SkyCool? Where's the best place to kind of reach out if they're interested?
Sure. And maybe I should have I will put my contact information here.
All right.
So
Oh, there we go.
that's my email
Great.
address,
Perfect.
website, and SkyCool's website is here. You can either email me directly, or the SkyCool website has an inbox where we monitor for things.
Okay, awesome, amazing. Well, everyone reach out at these addresses. We'll make sure to include them in the show notes. And yeah, thank you so much again for your time.
Thanks for having me. I had a ton of fun.
Yeah, all right, take care. Bye.
Bye.